Yeah, okay. So thank you very much for the invitation to speak at this seminar. Yeah, so today I'm going to talk about Weierstrass sets on finite graphs. So the goal of this talk is kind of finding a tropical analog of Weierstrass semigroups. So I want to start by first recalling the notion of Weierstrass semigroup, so sort of the classical side of the story. So let's first fix a smooth projective curve X of genus G, and let's fix a point P of my curve X, and I want to define this set H of P, which is the set of natural numbers n, such that there exists a rational function f of my curve x that is regular on every point of x set P, and it has order at P minus n. So P is a pole of order n, if you want. So this set, so in summary, this set H of P is recording all the possible pole orders of rational functions that have a unique pole at P. Okay, actually this set can be equivalently defined in another way. So we used here rational functions. I can use also the rank. So if I just record when the rank of divisors of the form np, so just n times the same point P. So if I record when the rank of such divisors increases, the set of natural numbers at which the rank increases is the same set H of P. So these are two equivalent definitions of what is called a Weierstrass semigroup of X at the point P. And yeah, a nice property to notice is that actually this set of natural numbers is a semigroup. And actually, so the name suggests this. And it is a semigroup since, for instance, from the first property, so the one using rational functions. So I have, of course, that the order at a point P of the product of rational functions is the sum of the orders. So from this observation, I can easily realize that this set is actually a semigroup. But there is another nice and interesting property, which is given by what is called the Weierstrass gap theorem, which says that actually the complement of this set in the natural numbers has cardinality exactly G, where G was the genus of my curve. Okay, and so this object H of P is a semigroup and has finite complement, and so these objects cofinite submonoids. So submonoid stands for just sub-semigroup with 0. I'm going to call these numerical semigroups. So the Weierstrass semigroup of a curve at point P is a numerical semigroup. Okay. So this observation prompts maybe a natural question, which was asked by Hurwitz in 1893. That is, which numerical semigroups are Weierstrass semigroups? So we know that Weierstrass semigroups are numerical semigroups. So then what happens if I take a random numerical semigroup? I ask myself, is this the Weierstrass semigroup of some curve at some point P? Well, the first correct answer, the first correct example was provided almost 100 years later by Weierstrass, who showed that, so he provided a numerical semigroup that is not, so it is not the Weierstrass semigroup of any curve. So this semigroup here cannot be constructed as I showed in the last slide. So it cannot be realized as the Weierstrass semigroup of some curve at some point B. Okay, and then actually there is no full answer to this question up today. So I mean, a characterization of Weierstrass semigroups seem a little bit hard. And this is actually still an active area of research. So just to name one, we have a recent work of Koteril, Pfluger, and Zhang that went on archive like 1 or 2 months ago, that certifies some the Vistras realizability of some families of numerical semigroups. So that this is just to tell you that this is a still active area of research. Okay, so this was for the classical side of the story. So if you have any questions, you can interrupt me at any time. Okay, so if there are no questions, then maybe we move to the tropical side of the story. So in 2007, Baker and Norine introduced divisor theory on graphs. And this was later extended by Gathmann and Kerber and Mikhalkin and Zharkov to metric graphs. And so metric graphs are thought to be abstract tropical curves. So tropical curves in which so that I consider them in a sort of intrinsic way without any embedding. And yeah, so then so this divisor theory is sort of analogous to the divisor theory that we have on curves. So it's a sort of tropical version of the divisor theory that we have on curves. So one natural question then will be to ask what would be the tropical analog of Weierstrass semigroups in these settings, in this setting, so for graphs. Okay, so this is sort of the guiding question of this talk. And in this talk, I will just restrict to graphs. And so here a graph will mean a finite connected multigraph with no loops. So here I'm allowing multiple edges and I do not allow loops. And a simple graph will be just a graph in this sense with no multiple edges. Okay. So next, I'm gonna just give an overview of this divisor theory on graphs. So let's take G, a graph with n vertices. A divisor on my graph G will be just a formal sum of the vertices of my graph G. So a divisor D will be written as a linear combination of the vertices P1, P2, Pn with some coefficients AI, where AI is some integer. The group of divisors of a graph will be denoted by div G, and it is just a free abelian group on the vertices of my graph. So just to show an example, so let's say I have this graph here, and I label the vertices P1, P2, P3, P4, and yeah, a divisor D could be 3P1 plus P2 plus P3, so that's a divisor. And so actually I can think of a divisor as being also some labeling on the vertices of my graph. So here I'm labeling each vertex of my graph with the corresponding coefficient that I have on the divisor. Okay, so in this case, this divisor D will be 3, 1, 1, 0. And yeah, it is useful to think of divisor in these terms as labeling integers on my on the vertices of my graph. Okay, so maybe a little pause for questions.
There's nothing for now in the chat.
Okay. Okay, so, and then next, what is linear equivalence in this context? So linear equivalence can be intuitively described using in terms of chip firing. So chip firing games is something that is studied in graph theory, and it's a topic that precedes this divisor theory on graphs, but it turns out that this is related to the this divisor theory. Okay, so linear equivalence can be described in terms of chip firing. So what is this chip firing about? So let's consider our previous divisor D, and I want to imagine these integers to be a sort of chips on my vertices, or maybe an amount of money that each vertex has. And yeah, these numbers can be also negative. So I think then the vertex is in debt, and then I want to do a sequence of moves, a sequence of chip firing, in which every move consists of selecting one vertex. So for instance, for this graph, let's select this bottom left vertex, and I fire it, meaning that this vertex will distribute one chip or maybe one money to each of its adjacent vertices. So after this move, what I get is that this vertex will go to 0, and then all the other vertices will increase by 1. Okay, and so this was just one move. Then I can imagine to continue this process. Maybe I select this top left vertex, and then I do the same thing. In this case, this vertex will go on depth. So because it will decrease by 2, so I will end up with a -1, and then I will increase the value by 1 of these 2 vertices. And so, okay, in the end, I obtain another divisor D prime of my graph, and this divisor D prime was obtained by us from D by a sequence of these moves. And so by definition, I say that these 2 divisors are then linearly equivalent. So in other words, 2 divisors are linearly equivalent if one can be obtained from the other by a sequence of such moves. Okay, so this was a very intuitive way of defining linear equivalence. And then let's proceed to principal divisors. So the analog of rational functions in this setting are functions that go from the vertices to the integers. So I'm associating to each vertex an integer. Okay, so this seems very similar to a divisor, but I want to think of this object as functions, so some different object. And then I can imagine the function to be actually sort of the same thing. So I'm just labeling the vertices with integers. But so this for me, for now, is a function. So let's say I start with this function that associates -1 to this bottom left vertex and 0 to all the others. So that's a function on my graph. And then the question is, what is the principal divisor associated to this function? And so again, I want to define this in terms of chip firing. So I can think of the coefficients of the function to be some sort of instructions of what to do, starting from the 0 divisor. So to construct the principal divisor of this function f, I start with the 0 divisor, and then I see that there is a -1 here. And so this will correspond to firing one time this vertex. So I do so. And so I will go here. I will have a depth of -3. And then all the other vertices will be increased by 1. And so I obtain this divisor. And then on all the other vertices, I got 0. So this means I have to do nothing. So I'm done. And so the divisor I obtain is, by definition, the principal divisor associated to this function f. Okay, so this was one first easy example. Maybe let's see another example. maybe a little bit more involved. So let's say that we have a -2 in the bottom left, -1 in the top left, 1 in the top right, and 0 in the bottom right. So what I have to do is a similar procedure. So let's say I start with -2. So this means that here I have to chip firing 2 times, and I do so. So I obtain -3, 1, 1, 1, and then again, and I go -6, 2, 2, 2. And then the next thing I do is chip firing this 1 time. And so this will go to 0, and I increase the other 2 vertices. And then here I got a +1. So it means I have to do a sort of reverse chip firing. So the vertex will receive 1 unit from each adjacent vertex. And so I will end up with 6, -1 here, and all the others. And then I got a 0 here, so I have to do nothing, and I am done. Actually, notice that the divisor that obtained at the end does not depend on the order with which I've done this chip firing moves. So I could have I could choose another order of these moves, and in the end I will get the same divisor. And so that's the principal divisor of this function in this case. Yeah, and you can imagine too, you know, that's a working definition, if you want, of principal divisors. Okay, and then I can also define linear equivalence with principal divisors by saying that just 2 divisors are linearly equivalent if their difference is principal in this sense. So it's given by it's the principal divisor of some function. Okay. So next, some notation. So with d of p, this will be just the coefficient of the divisor p at the vertex p. And then d will be greater or equal than d prime, where d and d prime are 2 divisors, if and only if this happens for all coefficients. And a divisor is effective if all its coefficients are non-negative, and the degree is the integer given by the sum of all coefficients of my divisor. So this terminology is exactly the same as the one you find for curves. So the analogy continues to hold. And then denote by d plus g, the set of effective divisors of degree d. Okay. Then next I want to define linear systems. And so these are exactly the same in the case of curves. So the linear system of a divisor d will be just a set of effective divisors linearly equivalent to d. Okay. And the next thing I need is rank. So the rank of a divisor d will be -1 if the linear system is empty, and otherwise the rank of d will be the maximum natural number d, such that the linear system d minus e is not empty, where e ranges among the effective divisors of degree d of my graph G. Okay, so while this first notion maybe of linear system is familiar, maybe the second notion of rank might be not as familiar, but actually if you do the same computation on a curve, actually you obtain exactly the same notion of rank that you had for divisors on curves. So this is actually the same, but maybe we are less used to it. And the reason we are using this definition for graphs is because the usual one, considering the dimension of the linear system, does not make sense, because in this setting, a linear system does not have a natural structure of vector space. So I cannot even talk about dimension. So in general, just to know, this will be a polyhedral complex, and if I'm not wrong, in general, this polyhedral complex is not even 4-dimensional. But anyway, these are just more technical details. So in general, you cannot talk about, in this setting for graphs, the dimension of a linear system. Okay, so this was a brief review of divisor theory on graphs. And then we are ready to give the main definition of the talk. So I recall up here the definition that we have seen at the beginning of, so in the first slide, and this was the definition of Weierstrass semigroup for curves. So we have this, we add these two equivalent definitions. So one with rational functions and the second one with rank. So the idea here for graphs is to do exactly the same. But in some sense, I cannot do literally the same. So let's see. So this definition appears in a work of Kang, Matthews, and Peachey from 2020. So let's take a graph G and let's fix a vertex P on my graph. I have two definitions. So the rank Weierstrass set, which is, you know, more or less the same as this second definition with the rank. So I'm just recording the natural numbers where the divisor NP of my graph increase in rank. And then I have a second definition, which I call functional Weierstrass set, which is natural numbers such that there exists some function such that the order of the principal divisor of f at p is exactly -n, and the coefficients are non-negative in all the other points. So this is actually the same condition as saying that sort of the function is regular on all the points except p, and yeah, this condition is exactly the same. So okay, so then it might seem a little bit, might be a little bit confusing of why I'm distinguishing these two cases. So in the case of curves, these were the same. So if you do these two definitions there, they define the same set and you call this Weierstrass semigroup. But for graphs, these two sets that I'm denoting also differently, so HR and HF, are in general not equal. So that's our first main difference. And so actually in the same work, Kang, Matthews, and Peachey proved that actually you can find a family of graphs in which the cardinality of the complement HF minus HR is, you know, arbitrarily large. So that's our first difference. And so that's the reason why we are separating these two notions. And so, well, after this, after realizing this, maybe a question would be, which one is the best? So which keeps which properties, what analogy hold, and what can we save from the nice situation that we have from curves? So one first thing is the following. So I can define the genus of a graph, which will be just the number of edges minus number of vertices plus 1. So that's the analogues of genus for curves. And then I have a tropical version of the Weierstrass gap theorem. And this holds for the rank Weierstrass set. So the cardinality of the complement of the rank Weierstrass set will be exactly the genus of my graph G. And that's a nice property. Unfortunately, this is not true in general for HF. So this is a property that I have just for the rank Weierstrass set. A second property is semigroup. And actually, I'm calling these Weierstrass sets for a reason, of course. So it turns out that HF is a semigroup, but in general, HR is not. So you see, these two nice properties of Weierstrass semigroup are kind of distributed, one into the rank Weierstrass set and the other in the functional Weierstrass set. So ideally, I would like to obtain both of them. But unfortunately, in general, this is not the case. So I want to show you briefly an example on which this HR is not, in general, a semigroup. So if you consider the following graph, and this is obtained by gluing a copy of K23, this one above, and two copies of K22, or if you want the fourth cycle, and let's call this vertex of degree 7 or vertex P. So if I compute HR of P, then HR of P is this set here. So it's 0, 0, 3, 5, 7, and then I have all the natural numbers. And well, this is not a semigroup because you know, I don't have 6, which is 3 plus 3. Yeah, so this is one example. And actually, so this example was constructed from a result that we will see at the end. And actually, that result allows me actually to construct families of these examples. So I can get as many examples as you want in which this HR is not a semigroup. Okay. So next, the first result that relates these two sets is the following. So this was conjectured by Kang, Matthews, and Peachey. So if you restrict to simple graphs, then in every vertex of my graph G, I have this inclusion here. So the rank Weierstrass set is contained in the functional Weierstrass set. So this result is particularly useful because from the point of view of computing these sets explicitly, because so in general this HF, so the functional Weierstrass set is relatively easy to compute. I mean, okay, it depends on which graph you have, but it is easy. Okay, it is certainly easier than the rank Weierstrass set. So the rank Weierstrass set is way harder. And so, for instance, one first example that you can see is if, for instance, you take the complete graph. So in the same work of Kang, Matthews, and Peachey, they found the functional Weierstrass set on every vertex. So I mean, the complete graph is has some symmetry, so every vertex, in a certain sense, is the same. And so the functional Weierstrass set in this case will be generated by n plus 1. And so you can do this explicitly. And then from the previous inclusion and the fact that you know what is the cardinality of the complement of HR, so it will be the genus and of the graph, of the complete graph. And in this case, this number is the same as the cardinality of the complement of this set. And so from this inclusion, it will follow that these two sets are the same. And so this is one example in which you can compute both. Okay. So yes, I mean, so this result was conjectured by them in order to do this procedure. So the idea was exactly this. And yeah, ideally, so you can do the same for the complete bipartite graph. So you use the same procedure. You first compute explicitly the functional Weierstrass set, and then you realize from the inclusion and by computing the cardinality of the complement, you realize that actually these two sets also for the complete bipartite graph are the same. And in this case, this set is this. So you have multiples of n up to the multiple n times n minus 1, where m and n are the cardinality of the two sets of vertices of the complete bipartite graph. And so this prompts natural question. So under which conditions on my graph G I have this equality here? So I mean the complete, so this happens for the complete graph and the complete bipartite graph, but these two graphs have asymmetry. So maybe when you have some symmetry, or maybe when the structure of G has some property, then maybe you have equality, which is a desirable condition, because then you will have both properties on the same set. So the complement being of cardinality the genus and being a semigroup. So that's an interesting question. And then, so next, I want to discuss a little bit about if we can somehow characterize these two sets. So the question would be which subset of the natural numbers are the Weierstrass set rank of functional of some graph. And so it turns out that actually in this setting, a very easy and natural construction that I call vertex gluing is very useful in this context. So essentially, this consists of you start with two graphs, you fix one vertex in each graph, and you glue them along the fixed vertices, obtaining a bigger graph with a fixed vertex. Okay, under this situation, it turns out that the functional Weierstrass set behaves very well, in the sense that the functional Weierstrass set at this vertex of this graph G will be given by the sum of each individual Weierstrass set, functional Weierstrass set at these vertices. So the HF at V1 of G1 plus the HF at V2 of G2. Okay, so this is a very nice property. And actually, this allows for a complete characterization of these functional Weierstrass sets. And so it turns out that all the functional Weierstrass sets of graphs are exactly submonoids of n, in the sense that every such object is a submonoid, and every submonoid can be realized as a functional Weierstrass set of a graph. And you have the same thing if you restrict to simple graphs, then these characterize numerical semigroups. So in this case, if the graph is simple, the complement will be finite. Okay, so the situation for functional is relatively easy then. Then you can ask the same question for the rank Weierstrass set. And so in this case, it is a little bit more technical. So let me first define this function lambda from n to n. This function lambda is defined from a vertex. And so lambda of k will be the minimum natural number n, such that the rank of np is exactly this number k. Okay, so this seems a little bit technical, but I'm actually recording the possible ranks of this divisor np. And so the reason why I'm defining this is to just express hr in other terms. So actually, this function lambda completely determines hr. So I can reconstruct hr from knowing this function lambda p. And vice versa, from knowing hr, I can reconstruct the function lambda p. Okay, the reason I'm using this sort of cryptomorphism for hr is because with respect to this ranks set hr. So in this case, the result will be the following. So I will use the same notation in the previous slide. So maybe let me recall the previous slide. So I have two graphs, G1 and G2. On G1, I'm fixing a vertex V1. On G2, I'm fixing a vertex G2. And then I obtain a big graph G, the vertex V. Okay. And so the result is that this function lambda on the vertex V of my graph G of K will be the maximum of sums of the first function lambda on G1 with respect to the vertex V1 plus the second function lambda on V2 on the graph G2 of K1 and K2, where K1 and K2 are ranging such that their sum is exactly K. Okay, maybe this is a little bit more technical, but the point here is that when I vertex glue, I can describe the rank Weierstrass set of the gluing from the graphs I started with. So that's really the point here. And how exactly this happens is a little bit more technical to write down, but essentially what I'm saying is this. And then from this result, I obtain a sufficient condition. So I don't know if there is a possible if a characterization for rank Weierstrass sets is possible. This is another possible interesting thing to investigate. So, but from this result, I obtain a sufficient condition. So the sufficient condition is as follows. If you consider any non-increasing sequence of integers, E1, E2, En, and then I define Si to be the sum from E1 to Ei of these integers, so these partial sums of this sequence. Then, and this sequence could be any. The only condition is it is non-increasing. And then after I make this choice, I'm sure that there exists a simple graph G with a vertex P, such that the rank Weierstrass set at that vertex P is exactly made of these partial sums Si up to Sn minus 1, and then I have all the natural numbers. And so this gives a sufficient condition because you are saying that certain subset of the natural numbers are realizable as rank Weierstrass sets. And this is also the result that was used to construct the example in which HR was not a semigroup, because you can easily take integers Ei in such a way that these partial sums do not form a semigroup. And the example that we have seen previously is if you take just 3, 2, 2. This will give you partial sums, and if you consider the partial sums, what you will get is something that is not a semigroup. Okay. Yeah, so this was the last slide, and I thank you very much.